Right, okay, so we were just told 2 talks ago that we shouldn't do Poisson solvers. That's solved, forget about it. We have done this, nobody needs to do it again. Right, okay, so what am I talking about? I'm talking about Poisson solvers. What are the issues? We already heard about this issue here for, they have very poor scaling, they suffer from starvation. But I think another issue is they're completely garbage that we're currently using. They're inefficient, and you can do better. You can essentially reduce the number of flops that we need to do. And I think we learned in this meeting, I learned at this meeting, that flops is not everything that counts. There's also energy. And I think this comes up later. So I think one should actually use efficient gravity solver, and one should also avoid the starvation problem, which is, I have more question answers here, I suppose, and the questions I have are highlighted in bold and purple color. So very quickly, why I think is inefficient. So this is what everybody uses, or almost everybody uses, is this an old code from the 80s, where you approximate the gravity on a particle by summing over distant groups. And of course, this is horribly inefficient, because if you have another particle nearby, you do the same job with the other particle again. This also introduces an asymmetry. The force from this particle here onto that particle is not computed in the same way as the force from this particle is on that particle. So that means that momentum is not conserved in codes like Gadget, for example. It doesn't conserve momentum, ignores basic laws of physics. So what can we do? If you think about it, in the tree code, we want to compute the Green's function from this particle onto from the sinc particle or source particle. In the tree code, what you do is you do a Taylor expansion on the source end and replace the P2P particle-to-particle kernel by a particle-to-multiple, multiple-to-multiple, and multiple-to-particle kernel or computation. And you Taylor expand the Green's function at that end. And it's important to realize that this interaction is local to the sinc particle. So it has to write to every sinc particle. Now, in the fast multiple method, essentially Taylor expanded both ends. So the sys is the same as before, but now you also have a Taylor expansion on the other end. You do a cell here, and you do a multiple to local expansion, and then local expansion, local expansion, local expansion to particle. And the important thing is that this is a non-local interaction. Right? It doesn't talk. It does not deal with local stuff. And therefore much more exascale friendly. And another important thing that comes on later is that these interactions are that go far between many, in distance, are completely unimportant for the total scaling of the problem. One view to look at it is this is just a disk of 100 particles, and I highlighted every direct interaction with a red line, every M to P kernel in the tree code with a green line, and every M to L kernel with a blue line. And you see this is what you do with direct summation. You get 5,000 in this case for 100 particles interactions. Here you get a few hundred in the tree code, and here you get much fewer in the fast multiple method. And I think this is not too important. The next one is what I really like in this way of presenting this is you think about it not in space, but you use some order of the particles. You order the particles, for example, along a face filling curve. So all the particles are ordered here. And this is only 100 particles in this view graphs here. And they are ordered here and here again. This is the same particles. And so each dot here, these are 4,950 dots. Each dot represents an interaction between two particles. And of course, we are interested in each interaction once. I could have the dot. The dot up here is, of course, the same as this dot with the particles interchanged. So in direct summation code, which is still used by a big community of people who do collision null embodied simulations, they compute each individual dot here by their computation. I mean, they can make this very vectorized and the GPUs and stuff, but they still do this n-square problem. And so how does the tree code look in this? The tree code looks like this, where now there's a difference between sources of gravity here and sinks. So here in the direct summation, it's not each particle is both source and sink at the same time, whereas in the tree code, no, it's not true. And there's a clear asymmetry here. So we have to, this green line here essentially is this, you see this block up here is a cell. A big cell is a quarter of the simulation, and we can compute the interaction from this cell onto a particle which is in the other part of the simulation in one, this is one M to L kernel here. The green line is an M to P kernel, right? And we still have to do direct summation for nearby particles. Or we have to make smaller, we have to split the cell into smaller chunks. And that's what a tree code does. And this is what the fast multiple method does. Instead, you go back to symmetry, so you don't have to go do this. You see this is clearly symmetric, and each of these symbols here is just one M to L kernel. You see that close to the diagonal where you have neighbors, space filling curve. If you're near in space filling curve, you're a neighbor, but if you're a neighbor, you may be far, and you can also be further away in space filling curve. That is why you sometimes find direct summation a little bit away from the diagonal as well, but mostly it's not. So you see that most of the work is actually here, and there's very little work up here. The boxes get bigger and bigger, and so this is reflected in the scaling. Okay, I'll come to this in a minute, but the thing, of course, because of symmetry, you preserve Newton's third law. You don't violate it, as the tree code does. And the nice thing is the scaling relation. So the fast multiple method has a scaling of complexity of the order n, or better. This is even better here. So this plot here is an old plot from a paper 11 years ago, where I plot the number of particles in logarithm against the computational time divided by the number of particles. So that if you have an n log n, you divide by n, it's log n, this is log n, this is a linear. So this linear line here is an n log n scaling. And the flat one would be of the order n. And here is the cost for the tree building. So you see this part here, which includes tree building, this is dominated by the tree building. And this here is sublinear, right? Let's come back to this a bit later. But the fact that the fast multiple method is scales like the order n essentially tells you that it's all local. It's completely dominated by the local forces of near neighbors. The distant neighbors are negligible. Whereas in the tree code, all scales, the cost per particle is log n, which tells you that all scales contribute equally to the force of the particle, the distance as the local one. So essentially, the FMM manages to make the distant cost of the distant interaction unimportant, which also implies that the amount of communication required to do them is much reduced compared to the tree code. And that should actually benefit FMM applications. Right, you also see that the tree building here, which unfortunately is unavoidably an n log n cost, may eventually, if you extrapolate that somewhere, meet, and then we are in trouble. Also, this is for computing the gravity. This is an old timing, of course, in old times, but you see, this is timing for doing all forces. If you only do a fraction of the forces, then you're dominated by tree building very early on. So that's a worry, and you may want to not build the tree every time, even though, in my opinion, this introduces an error of time in your simulation, which essentially is dangerous. You have to be very careful. Now, this is a little bit I was recently concentrating on. Nobody really does an optimal tree code or fast multiple method, So what you really have is numerical parameters. This is what you choose for expansion center of the cells. Which expansion order do you use? And what do you use for your multiple acceptance criterion? And of course, what you really want is you want to use these numerical parameters in such a way that you get a minimal cost at a given error. Now, there are various issues here. A is, how do you measure the error? What is the error? Of course, it should be something with a force error. So you can consider the absolute force error, which is essentially the error between the approximated force being FMM or tree, or whatever Poisson solver you have, compared to the exact one. And of course, the absolute error is absolutely meaningless. You have to normalize it somehow. You can look at the relative error. And the relative error, I thought, is a good idea, but it's rubbish as well, because the absolute acceleration can be zero, or it can be very small. For example, if you have if you have a star cluster, and you're only simulating a collisional model in star cluster, the particles in the middle of the star cluster essentially have zero acceleration. The acceleration in the middle of the star cluster is a pure random variable because it only depends on the nearest neighbors. And it can be very small, and you don't want to divide by a small number here, you know. So I think another way to look at it is using a scaled error. So you introduce a scale by which you normalize the error, which essentially is the absolute. If the right-hand side, we would have here xij over xij to the third, which would be the ordinary acceleration, and take the absolute value of that. So this essentially is the absolute value of the attraction between two particles, and I take the average of it. This, of course, you can also compute with the fast multiple method, and you can compute it to low accuracy very quickly. And so it would be a way to provide you this scale. But I'm not quite sure what is the right choice, and also not quite sure what margin of error is acceptable, for example, in collision null simulations. Clearly, a margin of error must be acceptable. And in collision-less simulations, we usually argue that you know, the argument is that we use an approximation method here because we have an error, an estimation error already. We have already an error because we only get the sample of the real distribution, and we have to live with an error that is essentially shot noise error in there. And so if we make another error, it doesn't matter. It's also not completely clear to me how to measure cost here. I mean, I used to just measure CPU time, but I think that's not necessarily right. One thing, there was 3 short choices on my last view graph. And one thing that I'm pretty confident I know, of course it has to do experiment, is the question, what is the optimal expansion center? There have been 2 traditional choices in the past. One is to use the cell center of mass, which I think is used in Gadget, I don't know, but traditionally been used in tree codes and also in my code. Or the traditional FMM approach is to use the cell's geometric center. I think neither of this is a good idea. Or let's put it this way, not necessarily. First of all, I think there's no practical benefit anymore of using the geometric center. Now, at low expansion orders, if you really only go up to first order or maybe second order, using the cell center of mass is useful because the dipole vanishes, and you, for example, at zeroth order, automatically get first order, and the trace of the quadrupole is minimized, and so you know the order that you neglect is essentially small. So that may be a good idea for very low order. But at high expansion order, that is not what you want. What you want is to minimize the neglected higher order poles. You want to minimize the poles that you have not taken care of. And these poles scale, or the power in these poles scales like the radius of a sphere that you can draw right at the expansion center and contains all particles to the power p. Now, if p goes to infinity, this essentially means you want to minimize that radius. So an obvious choice is the center of the smallest enclosing sphere, SES, of all particles in the cell. Computing that already takes n log n, so we don't want to do that because we have an LDN code. So you can do an approximate thing. You can compute the center of the smallest enclosing sphere of the grandparent spheres, the granddaughter cell sphere. So this is you can do the daughter cells, but using granddaughters is a bit more accurate. You can do this during the upward pass of the code. And that gives you an expansion center which minimizes the essentially the radius or the size of the cell in terms of the convergence criterion for the G code or the FMM code. Right, so I was then doing some experiments in order to see how the errors actually behave. So it's a very simple experiment. I choose 10 to the 6 particles from a Plummer sphere. I use the FMM dual tree walk algorithm using a very simple multiple acceptance criterion, where you just use a critical opening, and that's the standard one that is used. Rho is the radius of each cell, and R is the distance between 2 cells. So this is essentially the standard geometric opening criterion. I only considered the FMM interaction if the number of interactions caught is larger than p cubed, which essentially means we don't, if it's less, we would not do FMM, we would use direct summation. And then I can then do the M2L interaction between these 2 cells, and then evaluate it, and I can also do direct summation between the 2 cells, and I can then, for this particular interaction, I can measure, the error that this interaction has for each individual particle, and I can then find the maximum error, and I can find the maximum relative error, and then I can plot them. And this is what I get. So here, what I do is, it looks not so nice on the screen, but it doesn't really matter. You see most of the things. So here is the opening angle, this thing here. And here is the maximum total error normalized by the sort of mean error, essentially the mass of the source cell divided by the distance between the two cells. And here's the maximum relative error. So it's the error of the maximum of the error of the acceleration over the acceleration due to this single interaction for orders P 4, 8, 12, and 16. And the dots are the individual interactions. So each dot is another M to L interaction. And there are several lines in this diagram. These full lines here is a rigorous error estimate. You can prove that the error has to be less than that. But it's a very crude estimate, which I have used previously to improve the method. And you see this error estimate is hopelessly bad. You know, it overestimates the errors usually by an order of magnitude. Another thing you see is that the traditional fast multiple method approach of using essentially large theta, so essentially allowing an interaction as soon as it's converging, and use the order only to make it more accurate is hopeless, because essentially you're stuck here and you're trying to push down here. The cost essentially is proportional to theta to the power theta. No, so the cost is proportional to p to the power 3. Theta over p to the power 3, I think, is the cost proportional. So you don't really want to be. Turns out that if you want the relative error in each interaction to be below a minimum, so if you throw a line here and say you want all interactions below that minimum, then okay, you can have very different minimums. Then it turns out there's an optimal opening angle for a fast multiple method, which scales like interaction to the power cube, which is only true for the spherical harmonic version of it, and that's finally is 1 over e. But that's not really what you want. A fixed relative error per interaction does not imply that you get a good error in the end of the day, because this is a geometric opening angle criterion here means that the relative error of an interaction is controlled. But of course, the distant interactions are with bigger cells. So the interaction between two massive cells are far away. The average force in there is huge compared to the force between the small. So the error here, if you control the relative error, the error will be huge too. And of course, the total error in the end of the day is not the relative errors that sum up, it's the total errors that sum up. So you will be completely swamped by the big interactions that actually are negligible. So it's completely stupid to do that. You really want to be more accurate on these interactions that are anyway not very important in the budget of your costs. And that's what you can easily do. But currently, it's not completely clear how you do this. I found an improved error estimate, so maybe you should go back one slide. You see here, why do we do that? Oh, it's this. You see that these lines here are just power laws. There's just simple power law here, and they're already reasonably good error estimates. So you can essentially plot the ratio, or in this is a log plot, the difference in this plot between the actual point and these dashed lines. And if you do that, you get these dashed histograms here. And you see that they're reasonably wide. This is the standard deviation they get of the order of 0.4 dex. And I found an improved error estimate, which is the full histograms here, which is more accurate. It has a little bit of it sometimes underestimates the error. This is the tail here above 1. But it's much more accurate. It's about half in width, and it doesn't have this enormous tail of a completely underestimated. Sorry, what is that? The error is here overestimated. So this is a problem, because if you overestimate the error, you do too much. You do too accurate computation, which is completely wasteful, and you could have done much better by doing it coarser. So the idea is to use this more accurate error estimate in your multiple acceptance criterion. But I'm not quite sure how to do that, because as I said, you don't want a relative error, you want something else to control. It's not completely clear how you do this. The tree code, of course, suffers exactly from the same problem. And I bet there's at least a factor of few in here to gain, to obtain the same accuracy. And I think we should harness this factor. I'm implementing this currently only in memory machines, and this is a very quick guide. So this is again this diagram I showed before. And now suppose we have domains 1, 2, 3, 4. How we parallelize that? We can do it. We parallelize for split the work for things. This would mean we split it in these boxes, these blue boxes. But if only a few particles are active and live all in one domain, that's completely bad, because nobody else has anything to do. I think Gadget works the other way around. it splits in this way, but it's still bad. And now, how would you do this if you would do a direct summation parallelization? You can do it this way. The problem is then you have a race condition. So, this processor wants to write, and this processor all want to write into the memory of this machine. You can avoid that race condition by using this blocking approach, where you split the whole thing into this and this, these 3 blocks, and you can do these 2 blocks can be done in parallel because they don't write into the same memory. And this block, of course, you have to do further work on it. You split it again, and you can do these 2 in parallel and these 2 in parallel. And of course, this can be done recursively. And you can do it recursively again and again and again. The question is, which processor does which block? And that is, of course, a trick. You can do the same for the fast multiple method. So in the fast multiple method, we split in block 1 and block. These 2 can be done synchronously. And then these 2 can be done synchronously, and these 2, and then you can do this recursively. So essentially, there's a task-based parallelism that naturally lends itself here to the solution of this sort of problem. And I would argue that this is the way to go. So this is just a little bit of code, because we are in a meeting where this is allowed. So this is the dual tree walk algorithm that is used in the fast multiple method. Essentially, you start the whole thing off by dual walk on the root cell with the root cell. So you compute the interaction of the root cell with itself. And this is the algorithm, then it's a recursive algorithm. You can do it in a stack, but it doesn't matter. I think computer scientists love recursive algorithms. If neither of these nodes is active, you don't do anything. I mean, in practice, of course, you would never call it in this case, but it's just easier to show for me. Now, if the multiple acceptance theorem said, yes, we should do something here, you do the interaction. And this includes, don't do direct summation as a special case here, just keep it simple. If this is not true, if neither is true, then we have to split this interaction. If it's a self-interaction, as in this case, we essentially loop over all the pairs of children of this node, and we walk on all these pairs. Otherwise, if it's a mutual interaction, we break the bigger of the 2 cells up. So we loop over the children of A and walk again over the children of B. This is here is standard C++ code, so everybody should understand that. Here, we can now, in order to parallelize, we have to unroll this. So what I unroll essentially is this loop. Now, in order to make it simple, I assume a binary tree, so there are only at most 2 children. So we can walk this is essentially child 1 with itself, child 2 with itself, and the interaction between the 2 children. And here, we have just 2 in each case. In order to use this block thing, we have to unroll it again. And so instead of doing this, we essentially break up both nodes. When we get here 4 interactions, and we can now identify the blocks from before. This essentially is block 1, and that's block 2 for the big interaction. This is a mutual interaction. This essentially would be the block 2 and 3 in the previous diagrams. And of course, now we can parallelize that and write a parallel code here. And this would be legal C++ code if I replace the word task with the word threat. But I rather have the word task here because I think one should not think about task as threats. And so people, there have been computer scientists who published this approach, but they have not really, what I find frustrating about computer scientists doing this type of thing, they just demonstrate it works and then stop. They're not interested in about optimizing the error criteria. They only show, you can do this and you can parallelize it, but they don't demonstrate that you can, how the errors work, and they also don't demonstrate that it scales well, even if you have only, say 1% of all the particles active. So in practice, everything is, of course, a bit more complicated, and there are ways to deal with this. I would like to know how to port this to Exascale. So how do you do this task-based parallelism on Exascale? I think I'm very looking forward to Tom's talk on that. And I'm currently having a project where I'm implementing a fast multiple method for high accuracy and unsoftened gravity. So the idea is here, you saw that the errors before in this diagram, and the errors, they were all the way going all the way to the round of error limit. Okay, thank you.